So let us start continuing our discussion on acids. So we had definitely looked at the various reactions the acids have. What is the notion of pH and the pH indicators and all that stuff. Now we have also looked at what are the uses of some of the acids. We have looked at organic acids, which basically are acids like the acetic acid and the other acids like citric acid, which is available or which is present in the plants and fruits and so on, and what their uses are. We have also looked at the mineral acids like sulfuric acid, phosphoric acid, nitric acid, hydrochloric acid, and so on, and how they are used. Now, what are the effects of these acids? Right now, of course, the acids, the presence of these acids definitely has some effect on various aspects of our life. Now, I'm just trying to show you some of the effects. Right now, one thing is, now as I told you, the fruits and the vegetables that we use for cooking does have acids inside them, and some of the examples are things like acetic acid, formic acid, ascorbic acid, and so on, which are present in various vegetables and fruits. Now, what happens is that from many years, humans have been using copper vessels for cooking. Even now we use it, right? You might have seen your mother using copper vessels in your kitchen to cook food. Now, the copper, as we have seen before, and also the other substance which is used for making these cooking vessels is brass. Brass is in fact an alloy of copper and zinc. Alloy means it is prepared by bringing or by mixing the copper and zinc together in a specific proportion, and that actually is how the brass is prepared. Now, copper and brass utensils are used very often for cooking, and in places like India, which I belong to, we use both these metals, that is the alloy, which is a brass, and also copper for making cooking vessels. Of course, the other one is steel and iron. Now, if you look at copper, when you use copper and brass, since copper is present, the copper can react with the organic acids. So when you cook the food, since the vegetables that you're cooking may have these organic acids, those organic acids can react with copper and make copper salts, right? Which could be chlorides or sulfates or these kind of salts, and these copper salts are poisonous. It's not good if it goes inside your body, right? So what should we do? We should avoid this. Why are we using copper for making these utensils? Is because copper is a very good conductor of heat, right? And when you are making the cooking utensils, you want to make it with substances which are very good conductors of heat, which can withstand very high temperature, because we are actually putting a flame which will be in hundreds of degrees, right? So it has to withstand that high temperature. It has to be a very good conductor of heat. It should be strong, right? And all that, and so keeping all that in mind, copper is a very good fit, right? Our copper and zinc alloy, which is a brass, that's also a very good fit. But we have this problem because copper can react with the organic acid. So what was done was that we started coating the copper with tin. Tin is another TN. Tin is another the TIN. Sorry, not TN. TIN. Tin, which is actually metal, which can be used to cover up the copper, give a coating of tin over the copper or the brass, and then what happens is that then the copper is not coming in contact with the vegetables and the organic acids which it gives out while cooking happens, and in fact tin is not very reactive, right? Now, how the tin prevents that is something which you have to look at, because you have to look at what are the properties of tin, right? We'll look at that later. But by giving this tin coating, what we are preventing is the copper to react with these organic acids. So when people do tinning, now I want to show you how the tinning is done, right? How it looks like. So this is the process of tinning, right? So you can see what is happening is that the copper vessel is heated to very high temperature, and this gentleman is applying. You can see that he's having a pair of tongs, and he's got some kind of a sheet of tin which is folded together, and it slightly melts and it actually sticks onto the copper layer. So you can see already a layer of tin has been applied. That's why it is not looking, otherwise copper is brownish, golden brownish kind of color, right? And you don't see that inside. That's because already a tin coating has come in, because he has been doing this for a while, and so the tin coating has come, and now the tin is going to prevent the copper in coming in contact with its organic acids and reacting to form those salts. So that actually gives safety in cooking. You don't have those poisonous salts being being produced because of the reaction of the copper with the organic salt. So your stomach is safe and things are all hunky-dory, right? So that's what's going on here. So you can see tinning as a process, and he's kind of applying the tin over the now he's not doing that on the outside. Why? Because the outside doesn't matter, because you have the food material which is inside the vessel. So what you need to avoid is the copper come in contact with the contents inside the vessel. So that is tinning, right? So I hope you understood why we do tinning for copper and the brass vessels. The reason is because otherwise the copper can react with the organic acids which are there in the vegetables, and ultimately it can produce poisonous salts which can go inside your stomach and create havoc, stomach upsets and all that stuff, indigestion and so on. Alright, now the other thing which is an effect of acids is acid rain. Well, now this is actually a what you call the environmental calamity or an environmental hazard, I can say, which is happening these days because we are using a lot of fossil fuels like coal, right? Coal is something which we mine from the earth crust, and the coal is formed out of the lot of organic matters which has been lying below your earth's crust because of the dead materials of plants and animals and all that, which has happened across billions of years of the planet, and that has turned into coal and into crude oil and so on, and we are extracting that and using it as fuel for various purposes. And all these fuels, for example the coal, when it is burned, it produces gases like sulfur dioxide and nitrous dioxide. So you can see that nitrogen dioxide, and so when we burn, right, when we burn the fossil fuels like coal, it produces these kind of gases, sulfur dioxide and nitrogen dioxide. And what happens is when they go up in the atmosphere has water vapor, right? Atmosphere has water vapor, and what just a moment. Okay, let me just enable it again. Sorry for that. Okay, so it has got gases. This gases like sulfur dioxide and nitrogen dioxide is produced, and the atmosphere has water vapor, right? And what happens when water vapor, when the sulfur dioxide and nitrogen dioxide can combine with this water, and which is the water vapor, which is water in vapor form, that's what water vapor is, and they can combine. And as you know, when these non-metallic oxides react with water, what gets produced? We have already seen that, right? It produces acids. So in this case, the sulfur dioxide with water, water vapor can produce. So this can produce sulfuric acid. Right? It can produce sulfuric acid. What about nitrogen dioxide? I'm sure you would have guessed it by now. It can produce nitric acid. So now what happens is that your atmosphere starts having these droplets or particles of sulfuric acid and nitric acid, which has been produced because of all these smoke which is coming out of burning the coal, having the sulfur dioxide and nitrogen dioxide, that actually reacts with water, which is actually the water vapor in the atmosphere, and that leads to production of sulfuric acid and nitric acid, which is all there in the atmosphere. Now what happens is that when the rain falls, the rain droplets are coming down, and the atmosphere is now having sulfuric acid and nitric acid, and that starts dissolving in these water droplets, and slowly the droplets which fall will be acidic droplets. It will be droplets of dilute sulfuric acid and nitric acid. That's what's falling. Do you know one very interesting fact? Just besides this topic, the Venus as a planet has got a lot of sulfuric acid in its atmosphere. It's got a lot of sulfuric acid, and so in Venus the rain is always sulfuric acid rain. Interesting, right? Interesting point. Astronomy, if anybody is interested, go and look at Venus, right? And read about Venus. A lot of interesting things that are happening there. A planet in a big turmoil, and with a lot of acid everywhere, and extremely volcanic planet and so on. So just go and read about Venus. It's a very interesting planet, right? But anyway, that is besides the topic. But coming back to here, so the acid rain is produced because of this, right? So the when the water starts falling down, the sulfuric acid and nitric acid, which has been produced because of reaction of these oxides with the water vapor, starts dissolving in these water droplets, and then the rainwater which falls down starts having acid, or it's acidic rain, or it is nothing but what is called the acid rain. So it's an environmental hazard, and that's because of burning of all these fossil fuels like coal, right? So now what should we do? What we should do is, there are multiple things. First is reduce burning of all these fossil fuels as much as possible. That's one thing. Second is, when you are burning this coal, there are ways in which you can treat the coal where we can remove the content of nitrogen and sulfur and so on in the coal, so that when you're burning, it only produces carbon dioxide but doesn't produce sulfur dioxide, nitrogen dioxide and so on, right? So there's ways of purification, and also ways of treating the smoke which comes out after burning the coal in such a way that all these gases are removed from that smoke, so that when it goes out to the atmosphere, it doesn't have sulfur dioxide and nitrogen dioxide. There are ways of doing it, and that's what we should do. And the most important thing is reduce burning the fossil fuels as much as possible, right? If you don't do that, that is going to lead to acid rain. Now, what is the problem with the acid rain? What is the problem with acid rain? One of the key and the most critical problem of acid rain is how it can affect the agriculture, right? Because now when this acid rain falls into the soil is actually, what happens? The water starts going down the soil, and then the soil starts becoming acidic because all this acid is falling into the soil. Now what the problem is, the crops that you grow, that like wheat, the paddy, the soybean, the sugar cane, all these crops that you grow, it requires a certain level of acidity of the soil. That means the pH value of the soil should be in a specific range. If it becomes too acidic, all the crops will start dying, right? We'll look at that later on in terms of what that means. We are going to discuss that part later on about the soil pH, and I'm also going to say for different crops what is the expected pH value of the soil, right? And that is where the agriculture department comes to the various farmlands and does soil analysis. I don't know whether you've heard about that, right? They do soil analysis, and during the soil analysis, one of the key things that they try to determine is what is the pH of that soil. Is it acidic? Is it basic? What kind of crop are you trying to grow? Oh, okay, is this a crop that you're trying to grow here? Oh, sorry, your soil's pH is not right for that. So you need to do something to bring the pH value of the soil to that range which is okay for the crop, right? So the agricultural engineers do a great job in seeing that the agriculture happens right, and the soil has the right composition for the crop that the farmer is trying to grow. Alright, now, but acid rain, as I told you, has a big impact here because it actually affects because the acid, the rain starts having acid in the droplets, the water droplets falling, it actually starts making soil excessively acidic, and that can affect agriculture. Then there are other issues. For example, it can corrode when the acid rain falls on your rooftop and the metal sheets and so on. It actually can corrode because it is acid. It's got acid, right? So it can have big corrosive action. So acid rain is definitely a very, very bad thing to happen, right? And I have just explained to you how that happens. Let me actually quickly show you a video which also explains the same thing. So here we have, this is actually showing some industry where they're using excessive coal. All this is coal. They're using a lot of coal to burn to produce to produce a lot of heat energy, which probably may be used, for example, used in cement. This, I think, looks to be a cement factory. In cement factory, they use a lot of coal to heat the raw material, which is used to produce cement for certain types of reaction, and for heating, they use excessive coal. And this chimney, which is liberating, that actually will be also having things like sulfur dioxide and nitrogen dioxide, and all this is going up. So you can see that all this is going up, right? All the smoke which has got sulfur dioxide, nitrogen dioxide is going up, and then what is happening is it starts reacting with water vapor in the atmosphere, and also all the vehicle exhaust, right? All the vehicle exhaust which is burning the petrol and diesel, even that will have sulfur dioxide, nitrogen dioxide, and so on, which is excessively happening. More and more vehicles being used in all cities and across the world, right? Now all this turns to sulfuric acid, nitric acid, and all that actually remains in the atmosphere. Now when the rain starts falling, that is where we'll start having trouble, right? So when the rain starts falling, that all that sulfuric acid and nitric acid in the atmosphere is brought down, and that makes the soil heavily acidic, right? So and that is basically what acid rain is all about. I hope you've got an understanding of what acid rain is and why that is happening. Okay. Now let us get into bases. So we have looked at acids. I think you've got a very good idea of acids. We have looked at various types of acids: hydrochloric acid, sulfuric acid, nitric acid, phosphoric acid. You have understood their chemical formula. We have also looked at some of the behaviors of how they react with metals, metal oxides, metal carbonates, right? What is their pH value? pH value is ranging from 0 to 7. And we have looked at strong acids, weak acids, right? All these kind of stuff. So it's been fun learning about acids, and let me tell you, the acids are extremely important chemicals as far as industry is concerned, and we have also seen how some of these acids are used: the sulfuric acid, phosphoric acid, nitric acid, hydrochloric acid, how all these acids are used in the industry for producing various different substances. Now we are actually turning our attention to bases. Right? Now we did look at bases at a very high level before, and so what are bases? What are really bases? Right? Now bases are substances which are bitter in taste, right? And are having a very soapy feeling. You touch the base, it will be very soapy. In fact, if you look at the soap and the shampoo that you use in your bathroom when you take bath, they have bases, and you can experience that soapy feeling. Right? So they do have bases inside that, right? Now, what are these bases? Bases are typically metal oxides, metal carbonates, and metal hydroxides. So these are actually bases, right? So some people believe that bases are just metal hydroxides. Not necessarily. There are metal carbonates which are bases, metal oxides which are bases, right? Now, they're extremely corrosive, right? And it can produce, for example, things like sodium hydroxide, which is also called the caustic soda. That's what is the other name of sodium hydroxide. It's extremely corrosive. Actually, by chance it falls on you, it's going to make big burns, and it's extremely corrosive, a very reactive kind of a substance. So most of these bases are like that, but of course, just like acids, there are also weak bases, strong bases, and so on. We'll actually look into that later on. So what are some of the examples? Sodium hydroxide, potassium hydroxide, right? All these. So let's go into a slide. So what are some of the examples? So now all these you can see has got hydroxide. So these are all hydroxides. So all these are hydroxides. So sodium hydroxide, potassium hydroxide, magnesium hydroxide, ammonium hydroxide. All these are hydroxides, right? Now this is bicarbonate, right? And so that's another example. So this is bicarbonate. HCO3 is bicarbonate. In fact, we have looked at this already. And when you looked at the bicarbonate, how the bicarbonate reacts with an acid, we have already looked at that in the when you dealt with acids. So this is a bicarbonate, and baking soda has got sodium bicarbonate, right? The baking soda, which is used very often for in the baking industry for making bread, biscuits, and all that stuff, cakes, all that. When you want to bake, you add baking soda, right? And there's a reason for that. We'll look at later on, right? So this is again a hydroxide, so calcium hydroxide, and oxides. Some of the oxides are bases. So sodium oxide, this is actually an oxide. This is also an oxide. All these are in fact oxides, right? So all these are oxides. And this is sodium carbonate. So carbonate, right? I don't have space there to write it. All right. So hydroxides, bicarbonates, carbonates, oxides. Many of these metal carbonates, metal oxides, metal bicarbonates, and metal hydroxides, all these are examples of bases, right? Now, just a moment. Okay. So now, what are bases? What are bases? What is so much special about bases? Now, you remember the most special characteristic of acids is that when the acids are dissolved in water, it produces hydrogen ions, H+ ions, right? Now, the bases instead produces hydroxyl ions, OH- ions, right? So that is the main characteristics of a base. So the characteristic of base is that it produces hydroxyl ions. That's the main characteristic of a base. It produces hydroxyl ions, whereas the acid used to produce the H+ ions, right? So main different characteristics. So acid, when dissolved in water, right, and it used to produce the H+ ions. Here it produces the OH- ions. So that is a key difference between the base and the acid, right? Now, not all bases can dissolve in water. So it's not necessary that all the bases can dissolve in water. There are certain bases which can dissolve in water, and those are actually the alkalis. So if you look at, so that is what an alkali is. So the bases which can dissolve in water are alkalis, like sodium hydroxide, potassium hydroxide. All these are examples of alkalis. And if you go outside and say alkali, oh, that's a base which can be dissolved in water. That's basically meaning of alkali, right? So alkalis are bases which can dissolve in water. Those bases which cannot dissolve in water are not alkalis, right? Alright, now where do you find these bases, right? So you can find bases in toothpaste, right? It can be found in antacids, it can be found in cleaning solutions, right? All these contain alkalis. And we will actually look at, we'll later on look at what are the uses of bases and where all it is used and why they're used and so on in the course of time. So don't worry about that, right? We're going to look at it. Alright. So what are the classification of bases? So if you look at bases, bases can be classified based on their strength and based on their acidity, right? So how strong is a base and what is their acidity? If you look at in the case of acids, we can classify based on the basicity, right? And here it can be classified based on the acidity. All right, now let us look at this. So, bases of strength. Now, there are strong acids and weak acids, right? We have learned about it before. Similarly, there are strong bases and weak bases. Now, what is the difference? Exactly the same concept. If you look at a strong base will completely ionize. So if you look at sodium hydroxide is a strong base, and when it is dissolved in water, it completely ionizes and produces sodium plus ions and OH minus ions. So they completely ionize, right? So there will be heavy concentration of hydroxyl ions in strong bases, right? So examples is potassium hydroxide, sodium hydroxide. All these are examples of strong bases which completely ionizes when dissolved in water and produces strong concentration of hydroxyl ions. Right? Now, that is the concept of strong bases. Now, what about weak bases? If you look at weak bases don't ionize completely, right? So they kind of only partially ionize, and so due to that reason, the concentration of hydroxyl ions will be far lower when compared to a strong base. So examples is ammonium hydroxide and magnesium hydroxide and so on. So these are all again bases, but not strong bases, or weak bases, because they partially ionize, and so when they are actually dissolved in water, the concentration of hydroxyl ions is lesser. So that is the classification of bases based on, right? So I just want to also elaborate. So when you say ionize, what does it mean, right? Now just to write it down. So if you look at sodium hydroxide, NaOH, when it is dissolved in water, what happens is that it completely ionizes to Na plus and OH minus. So now, as soon as it dissolves in water, it actually starts forming the sodium positive ions and hydroxyl. It starts splitting into ions, right? So that's what we mean by ionization. Same thing I had explained in the case of acid, right? Only thing is there it becomes H plus ion, the corresponding anion, right? So that's what's happening. In the case of sodium hydroxide, it becomes the cation, which is Na plus, and the corresponding hydroxyl ion. So that's what's happening in the case of a base, right? Now, so we have actually looked at the classification of bases based on strength, right? Now let us go ahead. Now, what about bases based on the acidity? Now, acidity is totally based on the number of hydroxyl ions provided by each molecule of a base, right? Now, let us look at the bases. So let us look at sodium hydroxide. It can only give one hydroxyl ion, right? It can only give one hydroxyl ion, and so it is monobasic. Similarly, KOH, potassium hydroxide, only one hydroxyl ion, right? So again, it is monobasic, right? So, but what about dibasic? Now let us look at things like magnesium hydroxide. It's MgOH2. So one molecule can give two OH minus ions. Two OH minus ions. So it is dibasic. So it can give two hydroxyl ions. Similarly, copper hydroxide, CuOH2. Again, it can give two hydroxyl ions, right? So all these are examples of dibasic bases, which can give two hydroxyl ions. By every molecule can contribute two hydroxyl ions. So that's dibasics. Now, what about tribasic? What about tribases? Now, tribasic, I would like to give you two examples. One is aluminum hydroxide, AlOH3. This is a formula of aluminum hydroxide, AlOH3. This can give, one molecule can give three hydroxyl ions. Can give three hydroxyl ions. You can see three hydroxide. Another example is ferric hydroxide. Ferric. Now you should remember that the iron is an element which is multivalent. So it is ferrous and ferric. Ferrous has got a valency of 2 and ferric has a valency of 3. Right? Now we are talking about ferric hydroxide. So it will definitely be FeOH3. right? Because this has got -1, so -1 into 3 is -3. So it has to contribute 3 electrons, and so that means this is ferric, right? So this is ferric, and if you look at ferric hydroxide, it can give 3 hydroxyl ions, right? Can give 3 hydroxyl ions. So that is tribasic. So this is tribasic. This is example of tribasic, whereas this is example of monobasic, right? So that is basically what I want to tell. So monobasic, dibasic, and tribasic, based on the number of hydroxyl ions which can be contributed by one molecule of the base, we can classify that into monobasic, dibasic, and tribasic. All right. Now, how do you prepare these bases? Right? Now, what are the various ways of preparing these bases? And that is what I am actually putting down here, and we'll deal with each one of them with examples of reactions, and I'm also going to show you some videos of some of the examples which are possible when you're preparing these bases. Now, so the first is metal with oxygen giving metal oxides. Now, as I told you, metal oxides are also bases, right? Now, let us take some examples here. I want to first write the chemical reaction, and then I will show you the video, right? So let us first write the chemical reaction. That app seems to be having a little bit of problem. I will just restart it. What is happening? Okay. Okay, now let us take in some examples of metal combining with oxygen producing metallic oxides, right? Now, first I want to show you sodium. Oops, what happened? Sodium, right, combining with oxygen producing sodium oxide. Right? Now, I want to just balance this, so I put a 2 here, and then I put a 4 here, and I put a 2 here. So, this is an example where sodium is combining with oxygen, producing sodium oxide. So, this is sodium oxide. Sodium oxide. So, this is an example of a oxide being produced, right? Now, let us see how this really happens, right? So let us see a small video which actually shows this. Now this is sodium, and sodium usually is an extremely reactive metal, so we cannot, I can keep copper outside, no problem, right? But I cannot put sodium like that outside. It immediately reacts and becomes an oxide, right? So to keep the sodium as is, usually it is kept inside hexane. Hexane is an inert metal. It's not a metal, sorry, inert substance, right? Remember we discussed about inert elements. Hexane is an inert element. It doesn't react with anything. So here if you look at that jar, what has happened is that pieces of sodium is dipped and kept inside hexane so that it doesn't come in contact with the atmosphere, and it is in contact with hexane, which is an inert substance, so it doesn't react, and so sodium remains as is. It's a shiny metal. It can be taken out and we can just use a knife and cut it into pieces. So it's not a very rigid and strong like iron and copper. It's a little more softer metal, right? Now let us see how it reacts with oxygen. So what you have in this jar is oxygen, right? So let's see how it reacts. So they're taking the sodium outside, they're cutting it into small piece. Yeah, so that's what it is, right? And then take that sodium piece, right? Now here we go. And then they are going to put that into a jar which has got, they're going to heat it a little. They're heating it a little, right? So here they go, they're heating it a little so that the sodium melts, right? And it's hot, right? Yeah, but they need to make it quick because otherwise the sodium will start reacting with the atmosphere. So yeah, and then they're introducing that into a jar of oxygen. You can see that the sodium starts burning, right? So sodium is burning, and when it's burning, it is actually producing sodium oxide. So what has happened in this reaction? They just heated the whole, heated the oxygen, they heated the sodium a little, right? They heated the sodium a little, and after that, they introduced that hot sodium into a jar of oxygen, which they already kept. So they probably would have put a tube of connecting to an oxygen cylinder and would have put oxygen into that jar and then just put it using just sealed it using a cork. That's what you see. And then when after heating the sodium, they introduced that into that jar of oxygen, and the sodium started burning. The hot sodium started burning with oxygen, producing the sodium oxide. So that's basically what I wanted to show. All right. So now let us go ahead and look at a few more examples of formation of oxides, right? Now the other example which I can talk about is, now once you have the sodium oxide, what I can do is I can add the sodium oxide to water and produce sodium hydroxide. So how do you do that? Na2O plus H2O gives me NaOH, right? Now probably I have to balance, and I just put 2 here. So I can do that, right? First I can produce the oxide of the metal, and then I can dissolve that oxide in water to produce the base, which is the corresponding hydroxide. Same thing I can do with potassium too. So I can actually burn potassium. Potassium also will burn an oxygen like sodium, and it produces the potassium oxide. In fact, it's K2O, and this reaction is exactly the same. 4, 2, right? And then I can take and put 2 here, and then I can take this K2O plus H2O, which produces 2KOH. Same thing. So I can take the metal, burn that in oxygen, produce the oxide, take the oxide, dissolve that in water, and produce a base. So that is one way of producing a base, of preparing the base. So you can see sodium hydroxide and potassium hydroxide both can be prepared that way, right? Similarly, I can show you calcium, right? So same thing can happen with calcium also. So calcium can combine with oxygen to produce calcium oxide, right? Calcium oxide. Now I can put 2 here and I can put 2 here, so it's balanced. Then I can take calcium oxide and water to produce calcium hydroxide twice, right? So now this is how many? 2. Yes, this is already balanced, right? So this is the way. So I can actually have the metal plus oxygen, which gives metal oxide, right? And then metal oxide is dissolved in water, plus water gives me the base. So this can be used as a procedure to produce the base, right? Now I want to show you one more where I want to see from oxide how the hydroxide can be produced. So calcium oxide, if you have calcium oxide, similar process can be used for sodium hydroxide, sodium oxide and potassium oxide also, but I'm just showing the calcium oxide one, right? So let us look at calcium oxide. Assume that I have calcium oxide. Oops. Yeah. So if I have calcium oxide and water, right, I can actually produce the calcium hydroxide. So that's what I want to show you here. So this is calcium oxide and she's putting that in water, right? And you can see that the calcium oxide is reacting with water and now what are those bubbles? In fact, the bubbles, this calcium oxide is nothing but it's powdery, right? And so what is coming out is nothing but some air which is trapped inside the calcium oxide. That's what's coming out, right? So it's not really anything which is you know, yeah, so don't worry about that bubbles. It's not carbon dioxide or anything. It's just air trapped inside calcium oxide. Now the calcium oxide now is reacting with water, and in fact you can see that calcium hydroxide will be produced. And how we'll prove that is by using phenolphthalein, right? So it will turn pink after a while if you put phenolphthalein. So we'll see that that's what will be done, right? So she's going to put some phenolphthalein now into that, and you'll see that it turns pink, right? That is the reason why it's turning pink, is because the calcium oxide has reacted with water and calcium hydroxide, CaOH2, is produced, and that is why it's a basic solution now, and that's why phenolphthalein turned pink, right? So that's what it is. So I can actually take the metal and make it react with oxygen, burn it, react with oxygen and make the oxide, and take the oxide and try to dissolve that in water and form the base. So that is what I showed you, right? So that is one procedure. I want to also show you how the magnesium, right, can burn in oxygen. So you can see the magnesium is again a metal, just like sodium and potassium, right? Now magnesium we can actually go and buy magnesium from a shop. It is not as reactive as sodium. As I told you, sodium just can't be kept outside. It will immediately react, and you know, we'll lose sodium. It will become oxide or whatever, right? So it's extremely reactive. But magnesium is not as reactive as sodium, right? So we can actually go and buy magnesium ribbons from certain shops, right? And so here, this is nothing but a magnesium ribbon, right? And let us see. And this is a burner, and he's going to burn magnesium. He's going to show you that. So you see, and the magnesium ribbon starts burning, right? And then after burning, what is produced is magnesium oxide. To see how you can see how the magnesium is burning. And now what is there here? This is nothing but magnesium oxide. What is left with this magnesium oxide, right? Now this magnesium oxide can be taken and made it dissolve in water, and that will actually give us the magnesium hydroxide, right? Just like the calcium, right? So how will the reaction be? Let me just write that down. So magnesium will react with oxygen. Oops, sorry. Oxygen to give magnesium oxide, MgO, right? Because magnesium has a valency of 2, right? And so I put 2 here and then 2 here, and so that is done, right? Then I can take the magnesium oxide plus water, gives me magnesium hydroxide. This is already balanced, right? So that is basically what happens. And I've seen how the magnesium oxide can be prepared. By just burning magnesium in the presence of oxygen, magnesium oxide gets formed, and the magnesium oxide can be now dissolved in water to produce magnesium hydroxide. I hope this procedure is very clear. I showed you so many examples, right? Now let us look at the next. That is, I can actually make metal react directly with water to produce the oxide, right? So I want to show you that, right? So I can actually make sodium react with water right, and potassium react with water to produce the corresponding hydroxide. So let us see that reaction, and then I will show you a video, right? So how will that happen, right? So I can take sodium and make it react with water directly, and that actually produces sodium hydroxide and hydrogen, right? Sodium hydroxide and hydrogen. So let me just make this 2, 2, and then 2. I think that actually balances it. Yes, it does, right? So sodium is reacting with water, producing sodium hydroxide and hydrogen, right? Now same thing can happen with potassium too. So potassium also can react with water, forming potassium hydroxide and hydrogen. Same reaction, same way of in fact balancing it. All right, so these are examples of sodium, the metal reacting with water directly, producing the hydroxide and hydrogen. Right, now let us look at a video which in fact shows that. So now this is going to be an extremely explosive reaction because the sodium is a very highly reactive metal, right? So you can see what happens is that it tap 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 tap, all the sounds will be heard, and sodium hydroxide will form and hydrogen which is getting produced. After a while, because it's an exothermic reaction, the heat is being produced and hydrogen will start burning again, right? So you can see all that in this reaction. It's a very highly explosive, interesting reaction, I can say. So the sodium is poured, and see it's highly effervescent and tug all that. Why is it burning? Because hydrogen is being produced, and because of the heat produced, hydrogen starts burning. Did you hear that? It's very explosive, right? And so you can see that the sodium is explosively react with water, right, and producing hydrogen, and that hydrogen starts again burning because it's an exothermic reaction. A lot of heat is produced, and when there is a little heat, the hydrogen will catch flame. Why? Because there's oxygen available in the atmosphere. Hydrogen will start burning with oxygen, producing water. This is something that we already seen. Remember the bubble experiment with hydrogen bubbles. Don't forget that. All right. Okay, fine. So that is what's going on. So sodium reacting with water is highly explosive reaction, right? So that's what you see here. I have not heated. There's no heat provided. Just put a piece of sodium in water, and then that's it. So that's because sodium is a heavily reactive substance, right? Okay. So that is about, even potassium will react in the same way, in fact. Now, if you look at some other metals like magnesium is not as reactive as sodium. So, if magnesium has to react with water, you need to provide heat. You have to heat it up, and so if you look at reactions, I want to tell you at a very high level, two types of reactions are there related to heat. I want to just give you an example, just give you an idea of this. There is what is called exothermic reaction. And now what are these reactions? These are reactions where heat is produced. Heat is produced. Now there is another classification of reactions which is called endothermic reactions. This means that for the reaction to happen, we need to supply heat. We have to supply heat by using a burner or some way. We need to provide heat, supply heat for this reaction to happen. So these are the two classifications at a high level of reactions. Exothermic reaction, for example, this reaction that we just now saw between sodium and water is exothermic. It is liberating heat. There's a lot of heat being produced, right? Then there are carbon burning in oxygen is exothermic. A lot of heat is being produced, right, when the reaction happens. And there are endothermic reactions where you have to supply heat for that reaction to happen, right? So you need to keep it above a burner or something and provide heat for that reaction to happen. So the both type of reactions are there: exothermic reactions and endothermic reactions. Just besides a point, but I wanted all of you to know that, right? And this terminology of exothermic and endothermic reaction. All right, now let us go back and look at magnesium. So now the magnesium also can react with water, but it reacts with steam because it needs heat. If there is no, because magnesium is not as reactive as sodium and potassium, so it needs heat for it to react. So that is why we need the magnesium only reacts with steam, right? But the reaction is similar. So magnesium can react with water, producing magnesium hydroxide. Let me just write down that reaction too, right? So magnesium can react with water, producing magnesium hydroxide and hydrogen. Okay, now let me balance this. So here I probably have to put the 2 and we are done, right? So this balance. So magnesium is reacting with water to produce oh, okay, fine, sorry, there's a small mistake here. Magnesium is reacting with water to produce magnesium oxide, hydrogen, right? Magnesium oxide and hydrogen. And in fact, magnesium oxide, when it gets into water, it actually will behave as a base. All right, so this is already balanced, magnesium oxide and water. So there's another reaction where you can see that oxide is produced when the magnesium. Now only thing is this here, should be steam, not water, because as I told you, magnesium is not as reactive as sodium or potassium, and because of that it needs heat to be supplied. So let us just see this reaction now. So this is actually in fact magnesium. I told you that magnesium is available as magnesium ribbon. It's a metal, it's a shiny metal, right? And now let us, so he's taking a small piece of that magnesium ribbon, and okay, fine, so he's talking about showing conductivity. That's fine, leave it. Let's go ahead. Now you can see what you're doing. He's putting that into water, and then he's going to heat that water so that the water turns to steam, and then that reacts with magnesium to produce magnesium oxide, right? As is, if I had put sodium, remember what has happened when I put sodium there, right? It starts exploding and started reacting and producing hydrogen, and hydrogen started burning. Very eventful. Why? Because sodium is far more reactive than magnesium. But in this case, because of magnesium, we had to provide heat, right? And when it's providing heat, and because of the heat, the water is vaporizing, and that vapor, the steam which is being produced, the hot water vapor, is reacting with magnesium, and that actually can produce magnesium oxide. And you can see, as we are putting phenolphthalein, you can see that it's turning pink. Why? Because it's becoming acidic. And this magnesium oxide, so in fact what is happening is that the magnesium oxide probably is produced intermittently, and then but in fact the reaction is similar to the sodium and potassium, where the magnesium hydroxide and hydrogen is produced, right? But you can also have a scenario where magnesium oxide and hydrogen is produced. That again depends upon the kind of temperature conditions and all that we provide. So the reaction that we saw right now, magnesium hydroxide was being produced, and that is why when the phenolphthalein was put, it turned pink, right? So you can see the scenario, and there is also a differentiation that you can see, the difference in reactivity between that's tendency of reacting between magnesium and sodium. Sodium is far more reactive, and it didn't require any heat or anything for it to react with water and produce the sodium hydroxide and hydrogen, whereas magnesium, it needed heat because it's not as reactive as sodium. That is another different point that you have to understand. So different substances have different levels of reactivity, and that is again related to their atomic structure, right? And so everything boils down to that. Now the relationship between atomic structure and the reactivity is something that you have to learn in the course of time. So you will unravel those mysteries as we go into 8th, 9th and 10th standard, right? You'll be learning, and maybe beyond that. So don't worry about that, right? Alright, so we have seen the various ways of producing hydroxides when the metal reacts with water to produce the hydroxide and hydrogen, right? So in fact the magnesium also can react the same way. So in fact the video which I showed, it was MgH2O giving MgOH2 plus hydrogen. That's what is happening, right? So I have to put a 2 here. And this was in fact steam, right? Because we had to heat it. So that is actually, and then we put phenolphthalein and you saw that it's turning pink, and that shows that the magnesium hydroxide is formed. Alright, so we have seen one way of producing the metal oxides and metal hydroxides, right? Now the other way of producing a base is when a carbonate reacts with a carbonate is just heated. If you heat a carbonate, it can actually form the oxide, right? And if that oxide is dissolved in water, that can form the hydroxide, right? So you can see that is another way of producing the base. So by just heating the carbonate, so if we can actually heat a sodium carbonate, a zinc carbonate, or you can heat calcium carbonate, and all these will lead to producing the corresponding metal oxides and carbon dioxide. So let us see some example here. Right, so I heat zinc carbonate, I just heat it, and that gives me zinc oxide and carbon dioxide. Right, now I want to show you this experiment. So I'm just heating it, just heat the carbonate, and that produces. Now this can now be taken to water, right, and then we can actually produce the zinc hydroxide if I want. Right, so that is basically what it is. So as soon as you dissolve in water, it becomes a hydroxide and it becomes a basic solution. Right, now let us look at how this happens. Right, so a quick video on how that happens. So here what we have here is zinc carbonate. The zinc carbonate is being heated, and as you heat, and what you have here is the lime solution. And as you remember, when the carbon dioxide passes the lime solution, it becomes milky, right? So that's what you'll see here. So you can see it's turning milky now slowly. Why? Because the carbon dioxide is liberated, and what is left behind is zinc oxide, right? You can see it's milky. Why? Because the carbon dioxide was passing through this lime solution, and some chemical reaction happens, and it turns milky. And what is left behind here is zinc oxide, right? What is left behind here is zinc oxide. So that's a way of producing metal oxide, another way of producing metal oxide, and that metal oxide which is produced can actually be dissolved in water to produce the corresponding hydroxide or the base. Right? So this is an example of a carbonate being heated to produce the corresponding oxide and carbon dioxide. Same thing can be done also with calcium carbonate. Right? So I can take calcium carbonate and heat it, which produce calcium oxide and carbon dioxide. And then of course I can take the calcium oxide. Remember the reaction which I showed, right? So calcium oxide can be dissolved in water and calcium hydroxide is produced. Remember when the phenolphthalein is put, it turned pink, right? So all these are the ways of producing bases, right? So this is exactly the way the bases can be produced. All right. So one way is the metal reacting with water directly producing the hydroxide and hydrogen, and the other way is I can actually just take the carbonate and heat it to produce the metal oxide and carbon dioxide. And once you have the metal oxides can be dissolved in water to produce the hydroxide. Right? So this is the procedure for actually forming the bases. Alright, now let us just go back and look at the presentation and continue. So we have looked at all these, right? So metal oxide reacting with reacting with oxygen to produce metal oxide. We saw sodium reacting with oxygen, right? Same thing can happen with potassium, and once you have the metal oxide can react with water to produce a base. We have looked at sodium oxide, potassium oxide, and calcium oxide reacting with water to produce the corresponding hydroxide, and I also showed you videos of all these, right? Similarly, in certain cases, the metal can react with water to produce the hydroxide and hydrogen, right? And I saw sodium reacting with water to produce sodium hydroxide and hydrogen, and then it was a very explosive reaction, as you've seen, right? In the case of magnesium, it's less reactive in compared to sodium, so in which case, in the case of magnesium, it reacts with the steam. It needs heat for the reaction to happen. So we need to heat that, and it reacts with steam to produce metal hydroxide and hydrogen. And we saw that that the magnesium hydroxide was produced because we put some phenolphthalein and it turned pink, right? Then the other way is, of course, the sodium carbonate, the calcium carbonate and zinc carbonate. These kind of carbonates can be heated to form the metal oxide and carbon dioxide. We saw zinc carbonate being heated to produce the zinc oxide and carbon dioxide, and then these metal oxides can again be dissolved in water, as we've seen here, right? Dissolved in water to produce the base. So these are the different ways the bases can be produced. All right. Now, what about the general properties of base, right? So let us look at the next slide. So what are the general properties of base? What are the general properties of base, right? If you look at the acids taste sour, citric acid, lactic acid, all those taste sour, whereas the bases taste bitter. Again, never ever venture in tasting these things, right? Never ever venture. All right, let me just never ever venture in tasting these acids and bases. Very, very important point. You do it, it is in your own risk, because all of these acids and bases are extremely corrosive. I'm just repeating this point again and again so that none of you will try out such things unless always check with your teacher when you want to do anything. The nature is extremely corrosive. It can burn skin. It can cause accidents if it's not used carefully, right? Solubility, not all bases are soluble in water, but there are many bases which are soluble in water, and they are called alkalis, right? Sodium hydroxide, potassium hydroxide, all these are examples of alkalis, right? Then soapy touch, they're soapy feeling. As I told you, even the soaps and the shampoos that you use in your bases have certain amount of bases, so they are all basic substances. Detergents that you use for washing your clothes, they are also basic, right? Indicators, turns red litmus blue, right? It turns methyl orange into yellow, and it turns the phenolphthalein into pink, right? So these are all things we have already looked at when you looked at pH indicators. I hope you remember, right? If you want, you please go back and look at those videos if you're not sure or something is a little bit confusing. All right. And when they're mixed with acids, they neutralize. So they neutralize with acids to produce salt. We also looked at that experiment where there was initially, some sodium hydroxide taken into a test tube. Then when the phenolphthalein was turning pink, then we kept on adding acid. At some point, the phenolphthalein lost its pink color because all the base was, neutralized by the addition of acid, and so that actually proves that the acid will neutralize the base and salt is produced. Okay. So that is something that this neutralization is something I think we have already discussed, right? So I don't want to delve into that again. If you want, you can look at the neutralization discussion we had in acid. I also shown you a video where I showed the neutralization and the effect of neutralization, right? So acid and base neutralize, producing a salt and water, right? And we have also seen sodium hydroxide plus HCl giving NaCl and water. So I don't want to discuss that again. Fine. Now, what is the importance of neutralization? That is what I want to delve in more. Why do we need to do neutralization? Right? Now, one of the very, very key reasons this is used on a day-to-day life is for agriculture. As I told you, the crops are dependent on the pH value of the soil. I want to just show you some table here. Right now, this is the table which I want to show you, and you can see the various crops. Right, barley's pH, it needs a pH value between 6.3 and 7, which is probably slightly acidic, not very acidic. slightly acidic, almost kind of neutral, is what we need for barley, right? And clover is another crop. Then corn, right? Soybean, wheat. You can see wheat, which is very common crop that we grow, and soybean is another crop that we grow in India, right? Now all these needs a certain type of pH value. So the soil, if it doesn't have a pH value which is in this range, the crop doesn't grow well. The reason why that happens is, the availability of various minerals like nitrogen, phosphorus, potassium, calcium, magnesium, sulfur, all these which is very important for the crop to grow, depends on the pH value. Right, so that is what this table is showing. So what is the pH value? So if you see, if it's slightly acidic or slightly alkaline, that is where we have maximum amount of nitrogen, phosphorus, potassium. All these nitrogen and potassium and calcium, all those are extremely important minerals for the crops to grow. So you can see that they are all maximum available when it's slightly acidic or slightly alkaline. If it is more, then what happens is that the crop doesn't grow well. Right. So now what often happens is that the soil may be heavily acidic. Now that could be because there is a lot of fertilizers were used for cultivating different crops, and because of the usage of fertilizer, the acidity of the soil went up beyond the range that we talked about. Right. It is like if the desired pH is 6.5 to 7 and the pH becomes 4 or 5, which is heavily acidic, then the crop doesn't grow. Right? Or it could be because of acid rain, as I explained before. Right? The acid rain again increases the acidity of soil. So because of all this, if the acidity or the pH of the soil is more towards the acidic nature, then what happens is that the crop doesn't grow well. So what we need to do is we need to do something where the pH of the soil is made less basic, and there you can use neutralization. How you can make it less basic, less acidic? Less acidic, you can make the soil less acidic by removing those acids from the soil, right? And for removing those acids from the soil, what you can do? You can add some base, and that base can react with the acid, neutralize it. So that is where I am sure that if you are from a region where there's a lot of agriculture happening, you can go and ask some of these farmers. Do you use slaked lime or quick lime? Right? Slaked lime is calcium hydroxide, and quick lime, it's not lime, it's quick lime. Let me just correct that here. Right? Which basically can be produced in different ways, right? And you can even ask the farmers how they do that, right? So I can explain that in Malayalam because I am from Kerala, so I know those various substances which are used in Kerala for this purpose. But unfortunately, I cannot talk about Malayalam here because a lot of you may not be Malayalis and not from Kerala, so I cannot tell you that. But there are various naturally occurring substances which has got calcium oxide in it or calcium hydroxide in it, and they can be mixed with the soil. So what the farmers do, they bring that, right, like ash, for example, right? So so they bring that and then mix that into with the soil, and while mixing, what happens is that these bases starts reacting with the excessive acid which is there in the soil, neutralize it, and thus it will bring up the pH value, right, to the range which is favorable to the crop. Right? Now there are certain crops which needs alkaline soil. Right? So if the soil is so there are certain crops where if the soil is heavily alkaline, that doesn't grow. So I'm talking about now these crops that we discussed here. If it is heavily acidic, in fact it should be in a range, right? Now there are soil but it is slightly all these crops need a slightly acidic soil, right? Because it's below 7. So all the pH is slightly acidic, not a lot acidic. But there are soil conditions where the soil has become alkaline, right? So in which case you need to make it acidic. So what you can do is you have to neutralize a base. So there is excessive base which is there because the pH of the soil is above 7. So if the pH of the soil is heavily below 7, you add a base to neutralize the acid and make it favorable pH. Whereas if there are certain cases where the soil is alkaline in nature, where the pH is above 7, in which case maybe it's 8. in which case you have to bring down the pH value to the range which is okay with the crop. So in which case you have to neutralize a base which is in the soil, in which case you can add some acid, right, to neutralize the alkali. So these are all ways in which the soil pH is controlled by using neutralization, and that leads to better crop growth and better production in the agriculture. So see how the neutralization is used. So what you're learning is not just for earning marks. These are things which you have to know. Tomorrow, maybe many of you may get into agriculture, start growing crops, and you should know why we are adding stick lime or quick lime into the soil and mixing up. It's because you have to neutralize the excessive acid, right? So, see, don't you think the story is wonderful? Yes, it does. I'm excited. All right, now let us get into the next one. Tooth decay. Yes. Why do your parents say, my dear beta, my dear Betty, go and brush your teeth in the morning and evening? Why they say that? Why should you brush your teeth in the morning and the evening? Because you have to avoid the tooth decay. Now, what is tooth decay? I want to just show you a small video on what is tooth decay. Now, this video is showing a tooth decay. So now let me just mark it and show it. Now this is tooth decay, right? That is tooth decay. What is happening? The enamel, you see it's black in color, and you can see small, it be some holes inside your teeth. What has really happened? The enamel is gone. Now this is enamel. This white color is enamel. That is enamel. Now what has happened is something has eaten away all that enamel, and that is why you have this hole here. That's tooth decay. And now what happens? This is beginning of the death of the teeth, to be very frank. Now more and more of teeth will be eaten away, and after that the whole teeth is gone. And it gives you a lot of pain, it leads to infection and all that stuff, right? So that is what is tooth decay. Let's just go ahead and see a little more of this video. So you can see here again, there is another tooth decay here, right? So this teeth has got multiple tooth decay. So there's another tooth decay here. There's another tooth decay there, right? Again, another small hole which has happened. Now, why is this happening? How is this happening? Right? Now that is what we need to figure out. And see, the dentist is showing that it is really a hole by putting something inside it. That's tooth decay. And that's not good. That's going to smash your teeth soon. And the teeth is just going to vanish. So what your parents say is a very, very important thing that you have to do on a daily basis to look after your teeth. Now, the question is, how does this tooth decay happen? Now, that is where some science comes into picture. How does this tooth decay happen? The tooth decay is happening because when you eat food, some food may get stuck between your teeth, and then there will be always bacteria inside your mouth, and that bacteria starts feeding onto this food material, and at that point when it does that, some acids are produced, and this acids starts reacting with the tooth enamel, and then and because of that reaction, the enamel is being removed, right? And that leads to tooth decay. That's really what's happening. Now, how does a toothpaste help? The toothpaste has got basic substances like calcium carbonate. It's basic. So what happens? It starts neutralizing these acids. That's one reason, right? Now, the toothpaste does a lot of other things too, but I'm saying it also takes care of neutralizing these acids produced by the bacteria as it feeds onto these food material which is stuck between the teeth. Brushing, of course, helps to remove those food materials, right? So all that things which are stuck here and there within your mouth, between the gum and the teeth and all that stuff gets removed by the toothbrush as we brush it, right? And Also, the toothpaste helps to neutralize all the acids produced by these bacteria, and that actually helps in preventing your enamel being eaten away by these acids. Right? So that is what is actually happening, and that is how the toothpaste is helping you to prevent the tooth decay, and there again the neutralization has a role to play. Then the other thing which I want to talk about is acidity. You say, oh, I had some spicy food yesterday, oh my god, my stomach is burning. Yes, haven't you told that? Oh mama, my stomach is burning, oh man, it's fire inside my stomach, I just can't bear it. Why? Why is that happening? The reason why that's happening is because in certain situations when you have a lot of spicy food, for digestion, the stomach may produce excessive acid. Excessive acid, which is mainly hydrochloric acid. And what happens is that when there's excessive acid produced, then that doesn't get neutralized during the digestion process. That acid lies in your stomach, and then it starts, it starts kind of, what happens when the acid falls on the skin? I told you it forms burns. Same thing happens inside your stomach, and the stomach in fact doesn't even have the skin production. It is very more soft tissues, right? So what happens is starts directly reacting with the stomach wall, and then that leads to the burning sensation. So be careful with the food that you eat. As highly spicy food, similarly things like all these aerated drinks like Coke, Fanta, and all these things, right? Highly spicy food with a lot of chili powder and all that, right? Things like Lay's and Kurkure and all these kind of stuff, all these can actually produce high acidity, and it's not good, right? Similarly, the fast food that you eat out of all these restaurants, all these can actually cause heavy acidity. So first thing is avoid eating such food. It is only, it just gives you a nice feeling when it is in the mouth. It goes into the stomach, it creates havoc, right? Now, assume we end up with that situation. What do? You have antacid, right? One of the antacids that's typically given by doctors, what's called the milk of magnesia, and that's something called magnesium hydroxide. And most of these antacid tablets also have basic substances. So this base substances goes and neutralizes the excessive hydrochloric acid inside the stomach, and that is how, I'm feeling relieved, right? The reason is because that base, the medicine has got base, and that base is reacting with the hydrochloric acid, neutralizing it, and you're feeling good. So that is how the acidity is treated by the antacids, by having the antacids. So then there are some other uses of neutralization. You can see one is, the bee sting. Now I told you the bee sting is because of the formic acid, right? And so what you can do is we can apply some baking soda, which is sodium bicarbonate, which is a base, right? And now the base can neutralize the formic acid there, and that can give you comfort, right? The other thing is calamine solution. Calamine solution even also is basic, right? Lactocalamine is a commercial product which is pink in color. You might have seen it, which can again be applied, and that lactocalamine solution is base, and that base can neutralize the formic acid, and that gives you comfort, right? Wasp sting. Now wasp sting is basic in nature. Unlike the bee sting, which is formic acid, the wasp sting is basic in nature. So since basic in nature, you need to actually apply something which is acidic, like acetic acid, which is vinegar, right? I can apply some vinegar for the wasp sting, and that can neutralize the base, and that can give you comfort, right? Then what about treating factory waste? A lot of these factory waste which comes from the factories have got harmful acids in it. So what you can do is you can use things like Slaked lime and quicklime to treat this, treat the water which is heavily acidic, which is coming out of the plants, the manufacturing plants in the companies, and neutralize these acids, and then only allow it to flow out into the rivers and so on. Otherwise, what happens? If you just allow the acids to flow into the river, the pH value of the water changes, and as soon as the pH value changes, the fishes and all the organisms which is there inside the river starts dying, which is not good, right? So that is why we should avoid that. Do you know what does the sweat have? The sweat, in fact, actually has acids. The sweat that you you have, right? When you run around and jog around, what you come out, what the sweat which is produced by the body is slightly acidic, right? And that is why the soaps are slightly basic. It can neutralize the acidic content in your sweat, right? And of course, soap does a lot of other things too, and you learn about that when you learn surface tension in physics, where how it reduces the surface tension of water, and that actually even helps. So there are a lot of other things soap does, but this is one of the things which soap does. All right. So I think you got a good grasp of what are bases. We have looked at how the bases can be produced, and we have looked at the classification of bases. We have strong bases, weak bases. We have also classified it based on acidity, right? There's monoacidic, diacidic, and triacidic kind of bases, right, based on the number of hydroxyl ions which can be produced by the molecule. And then we have also looked at what is the importance of neutralization, and how the neutralization is used in agriculture, how it is used to take care of the how the toothpaste is using that concept, right? How the acidity in the stomach is treated, and also some of the other things that we looked at. So I think you had fun learning about bases and neutralization. Now, what happens when you are now? Let us look at how the bases react. What are the ways in which the bases react, right? What are the different ways in which the bases react? Now, first thing is, what happens when a metal hydroxide is heated? When you heat a metal hydroxide, what happens is that it produces a metal oxide and water, right? So that's what I want to actually discuss next. So let us take some examples. So now let us take some examples. Now let us look at what happens when copper hydroxide is heated. That produces copper oxide and water. Copper oxide and water, right? Now I want to show you this reaction. It is not a very fast reaction. It takes a lot of time to happen, and you need to provide a lot of heat and so on, right? But I want to show you how this reacts and how the copper oxide and copper hydroxide reacts is actually a greenish solution. It's a greenish solution, and let us see what does copper oxide look like, right? Now let us see this reaction where copper hydroxide is heated for a long time, and then it leads to production of copper oxide and water, right? So that's what I want to show you. So now this what you see here is copper hydroxide, right, which is slightly greenish solution, right? Now what you see here is, in fact, what he has done is he has taken some of this and he put it in a beaker and stir. It's got a stirrer inside. It keeps on stirring, and kept on a heater, right, which is heated beyond 100 degrees Celsius and kept for a few minutes. And then what you can see, what does it change? Now what you have here, which is brownish black in color, is copper oxide, right? So what has happened is that this copper hydroxide has got converted, after heating for a long time, has got converted to copper oxide, which is brownish black in color, right? So that is basically what happens when you heat the hydroxide for a long time. Then it gets converted to copper, the corresponding metal oxide and water, right? So that is actually the example there. I want to show you a few more examples. So copper oxide is one. Calcium hydroxide, right? So when I heat calcium hydroxide, again same thing happens. Heat, and that produces calcium oxide and water. Similarly, if you heat ammonium hydroxide, there is a difference. That gives me ammonia and water. Now ammonia is in fact is a gas, so it gets liberated. The ammonia just gets liberated. So when ammonium hydroxide is heated, that leads to formation of ammonia. This is ammonia. This is ammonium hydroxide. And this is ammonia. Right? So it produces ammonia, which is actually a gas. So it starts actually getting liberated, and water. Right? So this is generally what the reaction is. So metal hydroxide when heated gives usually metal oxide and water. Okay, so that's what happens when the metal hydroxides are heated. Now let us actually look at a few other examples. What happens when the metal hydroxides react with carbon dioxide? So that's the other example which I wanted to show you. So look at this particular example where you have calcium hydroxide, and what he's going to do is he's going to take a calcium hydroxide solution, right, and he starts blowing into that. Now why blowing? Because when you're blowing out, you're exhaling, and that air will have a lot of carbon dioxide in it. So so what happens is, as and when you blow more and more carbon dioxide starts reacting with calcium hydroxide, creating the corresponding carbonate and water. Right? So that's what's going to happen. Let me just write the reaction first and then show you the video. So calcium hydroxide plus carbon dioxide. Small change in color just to make it a little more colorful. I hope that's fine. Let me just make the color same. So calcium hydroxide plus carbon dioxide gives me calcium carbonate and water. This is already balanced, right? So the calcium hydroxide is reacting with carbon dioxide, giving calcium carbonate and water. Now let us look at this particular experiment, right? So so you can see that he is using phenolphthalein. Now what he is going to do is he's going to keep on blowing carbon dioxide, and then after a while, initially when he puts, there will be phenolphthalein in his put, it is pink in color. So that's what you see here. Initially, because it's calcium hydroxide, it's base, and so it's pink in color. Now you keep on blowing carbon dioxide through the solution. After a while, when you put phenolphthalein, you'll find that it will not turn pink. Why? Because everything has converted to calcium carbonate, and that is basically not basic in nature. Right? And so it will not turn the phenolphthalein pink. So now look at what he is doing. He is actually blowing carbon dioxide through that solution. Right? He is blowing and the exhaled air, as you know, has a lot of carbon dioxide. Right? So he is keeping on blowing into it, and still, slowly you can see that the pinkish color will reduce, because the calcium hydroxide becomes lesser and lesser, because most of it starts getting converted to calcium carbonate. Now let us see here. Now you can see that almost it's completely vanished. Why? Because most of the calcium hydroxide has been converted to calcium carbonate. Right? It's slightly still pinkish, but if he keeps on blowing for some more time, and you can see that, it has come down quite a lot. Now you can see that it is almost gone, completely gone. The pink color is gone. Why? So what has happened is, initially it was full of calcium hydroxide, then when he blew more and more carbon dioxide through it, more and more of the calcium hydroxide start reacting with carbon dioxide and becoming calcium carbonate. And now at this point, the situation is that it doesn't have any calcium hydroxide left at all. Completely just been converted to calcium carbonate, and that's why the complete pink color has gone. right? Why? Because the calcium carbonate is not a base. Calcium hydroxide is a base, right? So because of that, the pink color is gone. Interesting experiment, right? So that is basically, this experiment is showing how the calcium hydroxide reacts with carbon dioxide to form calcium carbonate and water. You can see that the pink is completely gone, right? Pink is completely gone. So that's basically what I want to show you here. So I hope you got an idea of how that reaction happens. I can actually give one more example, which is so I think that should be enough. So that is about the reaction. So one is about the hydroxides. When it's heated, it actually produces a corresponding oxide and water, and then when the hydroxide reacts with carbon dioxide, it produces the carbonate and water, right? So these are the two key reactions that which shows the reactive properties of hydroxides. Right, now let us go back to the presentation. Oops, where are we? So I think we have seen both of this, right? Let us go ahead. Okay, now what are the uses of these bases? How are these bases used? One very popular base is what is called the caustic soda, which is an alkali, which is sodium hydroxide. The commercial name of sodium hydroxide is caustic soda, and it is it's a very important chemical which is used for manufacturing soaps, detergents, paper. It's used in the paper industry, right? It is used for refining petroleum to remove the impurities in petroleum. And it is also used in producing fibers, the synthetic fibers like nylon, rayon, polyester. Polyester, I'm sure that you have heard. Polyester is used for making clothes too, and polyester shirts and all that you can get, right? And that's actually an artificial fiber, whereas cotton is a natural fiber which is obtained from trees, like cotton trees. Whereas polyester, rayon, nylon, all those are artificial fibers which are produced in companies where different chemical reactions are used, and one of the very important raw materials there is the caustic soda, which is sodium hydroxide, right? So manufacturing soaps, detergents, for paper industry, for manufacturing artificial fibers or synthetic fibers like nylons, rayon, polyester and so on, the caustic soda is used, which is alkali because it can dissolve in water. The other example is slaked lime, calcium hydroxide, right? We have already seen one use of it. It is used in agriculture to neutralize the excessive acids, right? We have already seen that, right? But it is also used in testing calcium carbon dioxide in labs. As you have seen, right? You have the slaked lime solution through which when the carbon dioxide passes, it becomes milky. And you've seen that being used many times in the videos, right? So to prove that carbon dioxide is emitted, you can use a calcium hydroxide, the slaked lime solution, or nothing but the calcium hydroxide solution. And when the carbon dioxide passes through it, it becomes milky because calcium carbonate gets produced, and that actually gives the milkiness into the solution. All right. But it is also used for whitewashing, and in many villages, actually, the slaked lime solution is used to give a coat to the wall and white coating to the wall. Then it is used for producing bleaching powder. What I have put there is, in fact, the chemical formula of the bleaching powder, which is calcium CaOCl2. Don't bother about it. If you're interested, you can remember. That is CaOCl2 is the chemical formula for the bleaching powder. It's used as a cleaning agent. It is used for bleaching clothes, right? Idea is basically it is used for removing dirts and stains from clothes and so on. The bleaching powder is used, and for producing bleaching powder, manufacturing bleaching powder, the calcium hydroxide is used, right? Slaked lime is nothing but calcium hydroxide, CaOH2, right? Then it is used in manufacturing of cement, right? That's another place where slaked lime is used. Then magnesium hydroxide is nothing but milk of magnesia, which is used as an antacid, right, for reducing acidity. I've already explained about what is antacid and how it helps in reducing acidity, where it neutralizes the excess hydrochloric acid inside the stomach, and that gives you comfort. Then ammonium hydroxide is another one which is used for manufacturing dyes, and also it is used for manufacturing the synthetic fibers like rayon, nylon, and so on. It is used in fertilizer industry for producing fertilizers. The ammonium hydroxide is very important raw material for the fertilizer companies, right? So that is actually about the bases. So we have looked at bases. What are they, how they can be prepared, what are the kind of properties of bases, and also how they react. And now we have also looked at some of the common bases, how they're used for producing certain products, right? Now I want to also discuss about salts. As we've seen, salts are produced when acids react with bases, right? So one example of that reaction is very common example that always is used, which is the sodium hydroxide combining with HCl, producing NaCl plus H2O, and this is a salt, and this is a base, and this is an acid, right? So this is a very common example which always is quoted when you talk about neutralization reaction where a salt is produced. Now when you look at the salts, there are again classification for salts. There are the normal salts, acidic salts, and basic salts. Now what do you mean by that? What do you mean by basic salts and acidic salt? Right, so what it means is that if you're using a normal salt, for example, sodium chloride is a normal salt, right? Now this, when it is dissolved in water, it gives a neutral solution. A neutral solution. Whereas, no, sorry, this I need to change this. Oops. There is a small mistake here. This is not normal base, this is normal salt. Small mistake, typo. Sorry for that. Okay, fine, done. Alright, so now what do you mean by a normal salt? What do you mean by a normal salt? What do you mean by a normal salt? When it is dissolved in water, it produces a neutral solution. Which means the pH will be 7. Right? It's a neutral solution. Whereas an acidic salt, when dissolved in water, forms an acidic solution. Sorry. It forms an acidic solution when dissolved in water, which basically means the pH is less than 7. And for a basic salt, it forms, when it's dissolved in water, forms a basic solution. Which basically means the pH is greater than 7. That is what it means. So the salts can be classified into the normal salt, acidic salt, and basic salt. And the normal salt, when it dissolved in water, forms a neutral solution where the pH is 7. Whereas when you have acidic salt, when it is dissolved in water, it forms an acidic solution where pH is less than 7. And for a basic salt, when it is dissolved in water, forms a basic solution where the pH is greater than 7. Now, how are these? Now, what are some of the examples of all these things? Right. So, what are the examples of a normal salt? Whereas, what are the examples of an acidic salt, and what are the examples of a basic salt? Right. Now, that is what actually we have to see. Right. Now, example of a normal salt. Example of a normal salt is sodium chloride or potassium chloride. All these are examples of a normal salt, right? Whereas an acidic salt, example of an acidic salt is sodium example of a acidic salt is examples of acidic salt is like ammonium chloride. Right? Ammonium chloride is an example, or ammonium sulfate, another example. I think I better don't use this. Or rather use the note than that, because it's giving a problem. So let us take examples of, so we are looking at normal salt. Examples are sodium chloride, potassium chloride, sodium sulfate. All these are examples of normal salt, right? Whereas acidic salt, or it's called acid salt, example is like NH4, ammonium chloride, right? Ammonium sulfate. All these are examples of acid salt. What about base salt? Base salt examples are like sodium carbonate, or another example is sodium acetate. This is actually acetate, right? Sodium acetate. So all these are examples of base salt. Now how are these actually formed, right? Now so let us look at how these salts are formed, right? Now if you look at a strong acid, right? Let me go back to the other mode, because I have written examples here. Let me just have that also here. So if you look at a normal salt, as I told you, examples is sodium chloride, potassium chloride, sodium sulfate. All these are examples of a normal salt, where when it's added in a solution, it actually gives a neutral solution where the pH is 7. And normal salts are usually produced when a strong acid reacts with strong base. For example, how is sodium chloride produced? Sodium hydroxide and hydrochloric acid. Both are strong. Sodium hydroxide is a strong base, hydrochloric acid is a strong acid. How is potassium chloride formed? Potassium hydroxide reacts with hydrochloric acid. Potassium hydroxide is strong base, hydrochloric acid is strong acid. So again, how is sodium sulfate formed? Sodium hydroxide reacts with sulfuric acid. Again, both are sodium hydroxide is strong base, and sulfuric acid is strong acid. So you can see the normal salts are usually produced when strong acid and strong base reacts. Always it produces a normal salt. Whereas when is an acid salt formed? Acid salt is formed when a weak base reacts with a strong acid. For example, ammonium chloride is produced when ammonium hydroxide reacts with hydrochloric acid. Ammonium hydroxide is a weak base, right? Ammonium hydroxide is a weak base, and that is reacting with a strong acid like hydrochloric acid. So there again, what you're forming is a acidic salt, right? So a strong acid reacting with a weak base forms a acidic salt, right? Now let us take another example. Ammonium sulfate. It is formed when the ammonium hydroxide reacts with sulfuric acid. The ammonium hydroxide is a weak base and sulfuric acid is a strong base. So the salt which is produced will be a Acidic salt. So when a strong acid reacts with a weak base, it forms an acidic salt, right? Now, so whichever is strong, corresponding type of salt is formed, right? Now, what about the other situation where a strong acid reacts with a weak acid, a strong base reacts with a weak acid. So when a strong base reacts with a weak acid, that forms a basic salt. So, for example, how is sodium carbonate formed? When sodium hydroxide reacts with carbonic acid. Carbonic acid is a weak acid. Sodium hydroxide is a strong base. So strong base is reacting with a weak acid, and so the salt which is formed is a basic salt, right? So where the pH value will be greater than 7. Sodium acetate. Now acetic acid, which is CH3COOH, I know that you have not learned about, you will not be learning about it right now, about these acetic acid and all that, because it's an organic compound and you learn organic chemistry, and organic chemistry is probably that you learn in high school, so don't worry about it, but I just want to show you an example. So sodium acetate is again acetic acid, which is a weak acid, is reacting with sodium hydroxide to form sodium acetate. Sodium hydroxide is a strong base, acetic acid is a weak acid, so a strong base is reacting with a weak acid, and that leads to formation of a basic salt, right? So that is basically what is happening, and that is how these different types of salts are being formed. So it depends upon how strong the acid is and how strong the base is when the neutralization is happening, and if they're both strong, then it forms a neutral salt, whereas one is stronger than the other, then the corresponding type of salt is being produced. Alright? Okay, fine. Now let us go ahead and look at the next thing. So now, how are these salts prepared? Right? How are these salts prepared? So the salts actually are prepared in various methods, and I'm actually going to talk about all these various methods for preparing the salt. Now, one way of preparing the salt is where the metal reacts with the acid. When the metal reacts with the acid, it can actually produce a salt and hydrogen, right? So okay. Now let us take some examples for this reaction of metal with acids.